Okay, hello everyone and welcome back to the class. So this is the ninth session of this GPU class, and today we are going to take a look at image processing. So this is also important for the final project because the final project is based on image processing. And so we'll be going over the concepts and we'll also introduce what is the final project. So from today onwards, you can start working on the final project. So I'll post it on Piazza as to what the project means and what you have to do. And we'll also go over it in today's class, like what things have to be covered in the project. And the deadline for submission of the project is 3 weeks after today. So does any the undergrads in the class, do you have any midterm exams coming up? Just wanted to confirm about that. Any of the undergrads who are attending the class have a midterm exams coming up? In general, 3 weeks is sufficient for the project, so I think it should be good for everyone. Let's see, we have a message. Okay, that's fine. So Micah?
Yes.
So you have an exam next week?
Yes, it's Wednesday.
Okay, yeah. So I think then you'll probably have to watch the lecture online, but it should be fine for the project because 3 weeks is sufficient. So,
all right.
Yeah. Okay, then let's get started with the class. So this is a brief outline of today's image processing and what is the final project based on. So first of all, why do we need to process images? There are a couple of different applications where image processing is quite important. The first is to enhancement and restoration. So say you have a very old movie and then you want to make it better in terms of quality. So this particular application would fall in the realm of image processing. So you can do things like improve the contrast and correct blurred images. So there are algorithms that do that. Then of course transmission and storage. So when you are transmitting video over a network, you can see different formats of videos. And so all of these, like compressing a video or making it decompressing a video, etc. So all of these would fall in the realm of image processing. So how do you compress, and there are different formats for that, and all of this again is part of image processing itself. Then of course automated recognition, right? So say you want to recognize something, maybe an object, maybe a person. So that's also falls in the realm of image processing. Then on evidence, right? So for example, you want to see that a document is true or not, and you know what a true document looks like. So instead of having a person analyze, the computer can itself analyze that and present that result to you. So you can also see if something has been tampered in the document, and there are algorithms that are available for that. And then of course there's watermarking. So you might have seen some documents with watermarks, and that prevent basically illegal content manipulation. So anyone who tries to copy the content, the watermark is automatically copied, so they're not able to directly copy without giving credit to the original authors. So in general, like let's say we have an image of 600 cross 800 pixels, and then without compression, this occupies like 1.44 megabytes. But normally on the web, we have the JPEG format. So that is a particular format of image that is more compressed than a regular color image. And you can see that the size reduces from 1.44 M to 89K. So it's almost 16:1 compression ratio. Similarly, you can have video in different formats and different compressibility. So compression is definitely one of the most important applications of image processing. Then here we have an image. So this process is called denoising. So you can see that the image on the left has a lot of noise, which I think is called salt and pepper noise, because that's what it looks like. And then on the right, you can see that after image processing, that image has been smoothed out. So this was particular algorithm. You can take a look at the link here. I think that goes over what is the denoising process. But basically, they're trying to remove this noise from the image and make it clearer. Another important, which is similar to denoising, is deblurring. So on the left, we have a image of a PCB board, which is quite blurred. And then after running over using it through or running the image through an image processing algorithm, we get a restored image. Another thing is, say on top, we have multiple photos which are separated. like the photos have been taken separately, and then we are trying to find a way to combine them together. So that is also comes with image processing itself. There are algorithms that can help you do that. And again, as I mentioned, digital watermarks. So you can see that here we have this watermark on the left hand, like this watermark. So that basically protects the document against illegal content manipulation. And then sometimes there are also invisible watermarks. So people may not be able to see it, but through the computer you can easily analyze that watermark, and that helps to also do the same thing. And again, so this is a very famous image you will see in many image processing textbook. It's called the Lena. And then so here they have the original Lena image on the left, and then they manipulate the content to generate a corrupted image. So there's like blocks which are corrupted. You can see it's like a checkerboard pattern, and then they run an algorithm through it for it, so which basically masks these errors. So you can see that the image on the right is quite similar to the one on the left. So basically they were able to remove the corrupted image using edge directed interpolation, which is a mechanism to remove or correct errors in an image. And again, moving from super or moving from low resolution to high resolution image, that also falls in the realm of image processing. So compressing, decompressing, etc. So this is just another image of what they are terming as face hallucination, again done through a computer using image processing. So another example, so here we have a aerial view from NASA. So you can see that after doing the image enhancement, so first picture on the left is quite cloudy, so we're not able to see anything. But after running different image processing algorithms over it, you can see that the image becomes clearer. Another concept which is important is image histograms. So that shows how the intensity of the image is varying. So for example, here we see that the histogram has a very high intensity on the left hand side, so that's a dark image. Then on the second image is a bright image, so that means that the histogram is more on the right hand side. And then we have the low contrast and high contrast image. So the histograms can be used to look at how the contrast of the image is varying. And there is an algorithm called histogram equalization that tries to resolve this problem. So if you have a picture where there's particular spots which are very bright and you want to rather even out the contrast, so then normally what they do is that they take the image histogram and then they run an algorithm called the histogram equalization. So yeah, that's what they're doing, right? So here they're trying to even out the image so that most of the all the image have like a more smoother appearance, as opposed to very bright or very dark, etc. So they're basically trying to smooth out the image. So now that we have taken a look at what are the different examples where image processing is useful, let's take a look at how image is represented in a computer. So we know, like for us at least, we see the picture, but the computer really doesn't understand what the picture is. It only understands numbers. And so people or the scientific organization have developed standards for how an image should be represented in a computing form that can be used for image processing algorithms. So basically we can think of it as a function f, right? So f of x and y would give the intensity at the point, and then we have this grid and we expect the image to be defined over a rectangle with this finite range. So we basically have this xy matrix, and then each point in that matrix would represent certain intensity. And then so that's for black and white, you have like this single matrix, right? So that's called a grayscale image, where every value in the matrix would vary from 0 to 255. And then so the 0 to 255 basically is a range of intensity. And then in terms of color image, it's just instead of like this one matrix, we have three matrices, so which is RGB. So RGB is red, green, blue. So these are the three different matrix that can represent a colored image. There are also two other things, I think they're called hue and saturation, but these are three more which are more important, the RGB matrix. So basically here you have the Terminator image, and then they're trying to represent it as a function. So we'll see over how the matrix looks in the later examples. So what is the pixel, right? So that's the most important part of an image. So pixel is the smallest piece of information that is understood by the computer through image processing algorithms. So I should not say understood by the computer, but more understood by the image processing algorithm, because the image processing algorithm basically manipulates these pixels, or tries to get some information from them. So the word pixel is basically stands for a concoction of two words, pix and l for element. So each pixel is basically it's a small point that represents a sample of an original image, and the more of these samples you have, the more accurate representation you would have of the final image. So the intensity of each pixel is variable. So as I mentioned, in a colored image you have 3 or 4 components, and in a black and white there's only like a single value which represents the intensity from 0 to 255. So in terms of computing, we usually operate on what is called as digital images. So the idea is to, we have this 2D space on a regular grid, and then we quantize this sample to the nearest integer. So now this image can be represented as a matrix of integer values. So you can see this 2D matrix, and then each point would represent an intensity in this matrix. So that's how images are presented to compute image processing algorithms, right? So this matrix of I and j, and then each point, which is a pixel, and which is the intensity of a particular pixel, that's represented here. So the next point is, okay, we understand how it's represented, but then how can libraries or any computing algorithms actually read this image, right? So the scientific organizations or industry have come up with different standardized means as to how image have to be represented in a computer. So there are different types of files, as you already have seen, like JPEG, PNG, BMP. So these are all different formats that have different applications. One is high quality, one is low quality but smaller in size, etc. So these formats basically have us. So when an image processing algorithm reads it, or when you read an image through an image processing algorithm, when you put a particular format, then it will basically decode that image into this matrix based on the format you provided. So every format has a standard on how things are represented, and then it falls back to the library to decode that image and form the matrix that you require. So again, which one is the best one? There's no direct answer to that, because that depends on what your problem is. But in terms of reading, like how can you read these formats? So you can of course write your own code to actually read these different formats, but it's of course like reinventing the wheel, which is not useful. So rather than that, you can use many libraries. So some of you might have used already MATLAB, and then OpenCV is the most popular one. So that they provide like a lot of libraries for image processing, and so you can use OpenCV to read these images, and they will directly convert it to the format into the matrix that you can process and run algorithms on. So it's easier to use a library than writing your own code to basically parse the entire image and get the data out of it. So one of the simplest version is called PPM. I think it's not that popular right now, but it's one of the more simpler image. So these were one of the oldest formats, I think, and they don't use any sort of compression. So the files are quite big, but it's easy to read the data because the format is very simple to understand. So the P2, so you can see that, this is on the top, we have this matrix, or rather I should say this is data. So there are different parts of the data. The first is P2, which means that it's a PGM. And the next two numbers, which is a 24 and 7, would give the width and the height, right? And the next number would represent the maximum value. So what intensity of gray is there between 0 to 255, for example. So it says that the maximum value is 15. And then black would be represented as 0, and the max value is white. And then we have the intensity of each pixel represented by a specific value. with the different pixels. So you can see like this is the main image matrix, and then each pixel has a value between 0 and 15, and that represents the intensity of that particular image. So you can see that the closer it is to 0, you'll see the more blackish the image will look. For example, the alphabet F is represented by the 3 values here, so the value 3, and as a result it is much darker, whereas P is represented by the value 15, which means that the intensity is higher. So any questions so far? Okay. So now we'll basically take a look at some code examples, try to see some basic algorithms on image processing and how they work. So the first algorithm is brightness, right? So that's to increase and decrease the intensity of the pixels by a specific value. So basically all the application does is going to go over the matrix, and then it will basically increase or decrease the intensity by a specific value that you can code. So we'll take a look at the code, and then just wanted to mention there's another material which I'll go over today. So that's related to this particular problem, which is how to manipulate the brightness using a image processing algorithm. So if you open your Piazza webpage, there's a session 9 supplemental material. So we'll be taking a look at that, because that the person who taught the class previously, he developed that, and that's quite useful to go over. So I'll just switch to that in a few slides, but just keep that ready. So the few things that are important is anyone here in the class who doesn't know what a makefile is? Anyone? I can explain it to you what it does, because it's a useful thing. So you can ask if anyone has a question about what a makefile is. But basically, a makefile is a simple way to make a code compilation easy. So say you have a lot of different files that you compile and then combine to form a binary, and then you have a lot of different libraries and linking parts that you include. And say you need to share your code with someone, right? So you can either send them all the commands that, hey, do this compilation, that compilation, and then that quickly becomes unmanageable as the project size grows. So a better way is to write a makefile, so that specifies how the compilation should work. So what are the libraries required, and then so makefile is part of the GNU specification. So they provide you basically, once you have a makefile and you run make, so that will basically compile all the code that is there in a project. So it's worth learning. You may not find it useful when you are just say have 1 or 2 files, but as the number of files grows, then it becomes much more cumbersome to manage, and that's when makefiles are pretty useful.
A quick question.
Yes. Yeah.
So this screenshot on the right is an example of makefile?
Correct. Yeah.
Okay, thank you.
Yeah. So here we have a code which has to do with manipulating the brightness of the image. In basic terms, right? So I won't go over line by line, but the basic idea is, first you can see that it's reading an image. Yeah, so it's reading an image and then converting the color image to grayscale. So grayscale is an image where everything is represented by 0 to 255, and then after that it's basically calculating the height and width. So these are all OpenCV functions, and then also OpenCV provides you with mechanism to read an input image from an argument, right? So this imRead, I believe, is also OpenCV function. And then what it's doing is that the first thing is the final idea is to manipulate the individual pixels of the image, and we'll take a look on the supplemental material as to what that actually means. But before that, I just want to go over this code. And then the function starts the GPU processing, so which is called GPU function, and then also does the same thing on the CPU. So we'll take a look at how the kernel looks now. So basically this particular GPU function is what's important to us. So here we have the GPU function. So what we are doing first, as usual, by now you know how you define the grid size, the block size, etc. And then it's allocating the arrays on the GPU memory, so the input array and the output array, and then it's calling memset, which is basically trying to set those values to 0 in the output. So this is something that you may not have always done, like the running the memset command, but it's usually recommended because sometimes the GPU memory might have some stale values, and then normally it's not a problem, but if it has stale value, then you will read the incorrect data. So it's good to run memset on your output matrix. Don't run it on the input matrix, because then you'll basically zero everything out in the input matrix. Like, don't run it after copying. You can run it here. So in this particular point, you can run CUDA memset on the input. But if you run it after copying the data to the GPU, then you will basically zero out all the values. So just keep that in mind. And then, we're defining the grid size, block size, and then calling the kernel. So pretty standard. You already know what are the basic steps involved in writing a GPU application. So that's what we are doing here again. So now if we take a look at the kernel, so again, reading X and Y, finding a location in the input matrix, and then reading that value, so which is the pixel intensity. And then it says that, if the value plus, if the value is greater than 255, then I keep it at 255, because 255 is the maximum value. So in a grayscale image, you cannot have a value higher than 255. So that's why if it says that the value is, if after incrementing the value goes greater than 255, then I'll just keep it at 255, because if you make it higher than 255, then you basically run into a corrupted image. So that the grayscale format doesn't exist beyond 255. Otherwise, what it does is that if the value is less than 0, then the value would be set to 0. And then otherwise, the third option is where the intensity is manipulated. So value is equal to value plus INC. And then, so this INC is a parameter that you pass to the kernel, right? And then finally, once that is done, the output value is equated to value. So that means that you manipulate the intensity wherever it was possible to do so based on the given conditions. So the quick question, if anyone can answer that. So this particular part, right, where this if else is present, is it good for a GPU or not? Can anyone answer that question? So what problems do you anticipate that will happen during GPU execution when running this if else? You can speak up.
Yeah, I can't really remember the name of what it was, but basically the threads, they won't all line up. So it'll be waiting on the ifs to finish executing. Correct. Before moving forward.
Yeah, that's good. So that's correct. So this is basically called branch divergence. So the problem is that, say you have so the warp is 32 threads, right? So if some of the threads take the if path, the other threads take the else if path, and the other takes the else path. So all of these three would be serialized. So this is a problem, and ideally you would want to avoid this, but it's not always possible. For example, in this application, it's important. So just when you're writing a kernel, always keep these things in mind. Like, you don't want to have a lot of if conditions, because that is going to slow down the execution. So if you have many different if else conditions, then it's going to drastically hinder the performance of the kernel, because a GPU architecture does not have any mechanism to speed up branches. So if this code was to run on a CPU, if else, it is quite faster, like individually per thread, because the CPU core has hardware to accelerate branches. So that's called a branch prediction. But on a GPU core, which is very much simplified, we don't have such mechanisms. So I'm going to quickly switch over to the supplemental material. So I think you should all open that as well. So can everyone see my new screen?
Yeah, we can see it.
Okay, all right. So the idea is, just go over this algorithm and what it does. So again, remember, we have this image, right? Say on this one is a globe, and then we are representing it in this 2D matrix. That's the height and the width, and then each value is a pixel intensity. So this is a grayscale image, so there's only one matrix. In a RGB image or a color image, you would have 3 different such matrices. So the other thing is that images are, of course, like any matrix is stored in row major. So just keep that in mind, like in C. So if you were to use Fortran, it's column major, but in C, it's all in row major. So that's the order in which things would be stored. So the basic idea of row major, again, I think we covered this maybe in the second or third class, is that elements that are in the same row are closer together in memory. So ideally, if you remember, we want always accesses to be coalesced. So in that case, row major is much more helpful. Oh, sorry, coalesced access is much more helpful because we don't want scattered accesses where threads in the same warp are accessing multiple different locations which are not adjacent in memory. So here, that's just trying to read how this matrix is being read. So to access a particular element in a matrix, in a 2D matrix, you need the X and Y, right? The coordinates. So again, just the 2D image here, right? So the 2D array, and any point in this particular 2D array, which is the X and Y, the position would be represented by, if you remember how you access a 2D matrix in the previous classes, that's the same way, right? So you have this, calculate this X position and Y position on the thread, and then you access that particular index. So for example, if I were to read X position 160 and Y position 55, then I would get the value that is stored here, which I think is 204. So that's the intensity at that specific point in the image. So again, just trying to show, how you're accessing this 2D matrix by just calculating the X and Y and then accessing that particular element in the array. So one thing to keep in mind is, how the width and the height dimensions and how it looks in terms of an image, right? So just look at the above figure for that one. So let's say we have this image. So this is basically a GPU card from NVIDIA. And then the idea is that you must subtract a constant value of each pixel. So basically convert this to this, something like that. So say you load the image, right? So that is the first step, as we have seen in the source code. So you load a particular image, and then you convert it into grayscale, because we are not dealing with color matrices here. We just work. The plan is to basically work on a grayscale image, which is what that code was doing. And then we are defining our block sizes, which is the tile size here. So threads in the block for Y dimension and X dimension. And then say we have a grid dimension, right? 6 and 6. So that means that's how the threads will be divided between the blocks. So you can see that the red squares some of them are going beyond the boundary of the image. So in your code, you actually need to take care of that, because these the ones on the boundary or beyond the image boundary should not be doing anything, right? But they exist, and so you need to ensure that those threads don't do anything that is trying to access that image. Because if the threads that are out of the boundary here try to access any element in the matrix, it would cause the application to fault, because even that memory does not belong to you. So the reason why we do it is that we want, for alignment purposes, right? So you can allocate on the GPU the full area covered by blocks. So if you remember the first example that we did, which is a vector addition, we had a if condition that says that if TID less than n, only then add. So similar conditions apply here, right? So you don't want to go beyond the boundary of what is allocated to you, but because you allocate your grids in such a way, to ensure alignment, you need to take care of that. So again, threads in the red area should not do any work. That allocated data will never be touched, right? So sometimes it might actually work, like your application may not crash, but it might run into some weird problems. So just beware of doing that. So now you can play around with different grid sizes. So if you have like a 13 on the x-axis and 14 on the y, then you can see that now each block is working on a smaller group of image, or smaller portion of the image, right? But so it's not only with experience you'll know which one is better, which one is worse, like what grid sizes and block sizes perform best. So I think you have already done many experiments to show how these things impact the performance of an application. So here in the kernel, right, so we have this block index 2 and 4, and we're trying to access a particular element in the image. So that's where we calculate this x and y. So tile size is basically block size, and we're calculating the x and y so that we can access a specific element in the matrix. And then once we have that, so that is what we call as the location, right? So then we access that location and then store it in a variable called value. So which basically takes the value at this 2 and 4 location here. So now once we have access, so then we go back to our algorithm, which we already covered, right? So based on what the condition is, you would be doing either of these 3 operations and then storing it in the output. And then eventually if you run this modification kernel, so I think you should all try to run it like once you have free time, or maybe you can run it tomorrow in the lab time as well if you finish early. So just take any image and then run this algorithm over. So the source code is already there in the slides. I'm not sure if there are .co files available for this, but I'll check, and if I find them, I'll post them on Piazza. So you can just play around, try to run it multiple times and see what happens, right? So you can basically keep running the brightness algorithm, intensity, and see how the image changes. So that's a good first experiment to do in case you're interested. So yeah, just a comparison showing what happened. So we had the original color image. Once we converted into grayscale, it did not look good, right? So you can see like seems quite weird. But then once we ran our brightness intensity modification algorithm on top using the GPU on a GPU image, ironically, we were able to get a much clearer image, which looks much better than the one in the middle. So yeah, I'll stop sharing this. Any questions about this particular example? Okay, then I'll go back to the slides. So again, you can see that this particular kernel was quite simple, but you already learned a lot of different optimizations that you can use. So maybe think about how you can leverage shared memory, constant memory, texture memory, etc. So, or maybe you can do like more processing per thread. These are different kind of optimizations that you can try out and see how they would impact the performance, because they will impact the performance, but without trying it out, it's not always clear which one will perform better. But you can try to think of it, see how the algorithm looks like, and then come up with your own solutions on that. Or maybe so you can remember that the matrix is stored in global memory, and so if you you can think of ways in which you can bring in more data on each read. So that's the brightness modification example, which is quite simple, but it goes over how so that all the image processing pipelines are very similar. So you use some library like OpenCV to read a particular image, convert it into your desired format, and then do the allocation of that array on the GPU, copy the data, and then run the kernel, and then analyze the final output, right? So it's all image processing algorithms, regardless of their complexity, will have the same pipeline. So now we'll come to Sobel algorithm. So the Sobel algorithm is used for edge detection. Does anyone know what edge detection is? Okay, so the idea with edge detection is that you can find, you were trying to see like what are different objects in an image, right? So you're trying to locate their edges, and then you do that by comparing the difference between neighboring pixels. So that way you mark an edge. So say if you have a table, and on a table you have a computer, you have a coffee cup and a bottle of water. So for if say you want to develop an algorithm that wants to identify if there is a coffee mug or not. So the edge detection algorithm comes in important play here, because the idea is that if you can identify the edges, so you can identify the different objects in the image, then you can run some post-processing algorithm on top to specifically identify that. But regardless of what you do, the edge detection is always done, or most of the time it's done prior to running any special algorithm, because that has to be done to understand how the image is separated or how the objects in the image are separated. So basically idea is look for edges in both horizontal and vertical directions, and then you try to combine them into a single metric. So these two matrices are the X and Y. So these are like masks that you apply on each pixel, and then you try to calculate. So once you have this X and Y, you'll get a value, and then you calculating the magnitude, which is root over X squared plus Y squared, and then the edge direction, which is tan inverse Y and X. So that's part of the algorithm. That's how they designed it. So let's say you have this stop sign here, and we run the edge detection algorithm. So it will look like the thing on the right. So you can see that it has clearly defined each separate object, right? So basically try to demarcate the boundaries between different objects that are present in this image. So you can see that all the alphabets are separated clearly, and then also the board itself has distinct edges between and the boundaries are clearly defined. So again, if we take a look at how the function looks, it's like very similar to the previous one in terms of the pipeline. So you always read the image, and then so they're also processing on the CPU. I'll go over the GPU kernel side because that's what's more important to us. But basically, they are trying to apply the X and Y mask, and then calculate the magnitude and the direction, and then calculate the edges accordingly. So here's the GPU function. The first part is of course very similar, doing CUDA malloc, memcopy, and then defining the grid size and the block size, and then launching the kernel. So the kernel is what's more interesting to us, because the rest of the part looks very similar to the example that we just took a look at. So here's the kernel. You can see that it looks slightly complicated than the previous one, and it is. So in terms of like reading the input, it stays fairly similar. So you're still calculating X and Y, calculating the location to identify a specific point in your matrix. And then here we are doing, if the thread is out of image range, so it doesn't fit, so that the if condition that I talked to you about, then you would exit. Otherwise, what it does is that it calculates these two values, so which are called sum1 and sum2. So what it's basically doing here is that it's looking at the boundary values, right? So if you remember the mask that we have in the previous one, right? Let me pull it up again. So these two masks will be applied, right? So just keep this in mind. So it's basically applying these two masks to calculate sum1 and sum2, and then calculating a magnitude based on that. So first it's applying the mask 1, and then the second mask, right? And then calculating the magnitude value based on that. So the magnitude is root over X squared plus Y squared. So the X is sum1 and the Y is sum2. And then it's basically running this thing that's saying that if magnitude is greater than threshold, then so the threshold is specified in this particular call in the kernel, and then says that if the magnitude is greater than threshold, then the location is set to, or the value of the output matrix is set to 255, otherwise it's set to 0. So basically using this algorithm, you can identify the edges that are part of your part of the image. So these two particular function looks quite big, because you're just applying this mask, but it's fairly similar if you just compare it to the mask that the X and Y mask. So that's what's being applied for sum1 and sum2. So just go over those two masks and compare this code, so that way it's easier to identify. So any question with regards to the Sobel algorithm?
That big function over there was pretty much just a matrix multiplication, right?
Yeah. It's basically applying this mask over that value, right?
Oh, sorry, mask. So it's not
Yeah.
matrix multiplication, it's a dot.
Yeah,
Okay.
so it's like taking a value and then multiplying it against the mask and then calculating this to sum one and sum two, right? So if we go to the mask again, yeah, so it's basically, so if you just take a later when you look at the code, later when you look at the code, just compare these two mask values and you can see how it correlates with that code.
Okay.
Yeah, it's easier to show if I had a whiteboard, but on online it's hard to show it like right.
I gotcha.
Yeah. So let's talk about the final project, and I'll post it on Piazza as well. So we already covered it in the introduction today, right? The idea is the idea is to develop a histogram equalization image. So the basics of image histogram, which we already discussed briefly, is that it's an algorithm that is used to pre-process image. So the idea is, you have an image where the intensity is quite varied, across the image, and so that makes it look ugly. So what we're trying to do is basically normalize the histogram so that we can even out the contrast, and then the image looks much better. So in terms of, if you look on the right hand diagrams, like the graphs, so in the first one we have this huge peak in a particular value, so that means that most of the pixel values are located in that range. But once we run our histogram equalization, then we convert it into a transformed histogram. So you can see that now it's much more better spread out, so that's much more smoother. Whereas in the previous one, it was all lying in one intensity zone, which is why the image does not look good. So the algorithm is, first you need to calculate the histogram of the image, then you need to calculate PMF of the image. I'm not sure what the full form is, but it's basically histogram by the total number of pixels. And then you calculate the cumulative distribution function, which is can be thought of as a prefix sum that we covered last class. And then you calculate the CDF into 255 to obtain the new gray level values, and then use the old gray value and map it into this particular array to obtain a new value. So ideally, you're trying to normalize the histogram and then equalize it across the entire image so that you obtain a much smoother image. So this is how the algorithm looks. I mean, there are plenty of resources available online on, I think I'll also post some videos as well, like on other platforms, which show what a histogram equalization is. But the algorithm itself in general is pretty similar. It's just that, can anyone think like why histogram might be challenging to implement on a GPU? So, in basic idea, histogram is just binning, right? So say I give you 100 numbers and I told you to bin all the numbers between 0 to 10 in ranges of 10. So all the numbers in 0 to 10 fall in bin 1, all the numbers in 10 to 20 fall in bin 2, etc. So what is the biggest bottleneck in doing that, right? Anyone with a, yeah.
Would it be that you're going to be accessing memory kind of randomly, since it might not line up? So if you're filling up one of the bins, you might be putting stuff in from a bunch of different locations.
No, like you mean, are you saying in terms of reads?
Yeah, I guess so.
So in terms of reads, it's fine, right? Because say you have this matrix. So say I give you just an array. Forget about 2D matrix. Say I give you just a single vector of 100 elements, right? And each thread reads one element from the vector, right? So this vector is in memory. It's like adjacent, right? All of the elements.
Mm-hmm.
So that means that read is not the issue. But think about what the write has to do, like how the binning part, what it's trying to write into an output matrix, right? But does anyone see that or get the idea that when you are writing into this output matrix, different threads will try to write to the same location? So because the output matrix, so say my first value of the vector is 10, oh sorry, let's say 5, and the 58 value of the vector is also 5. So the thread that processes the first value of the vector and the thread that processes the 58 value of the vector are both going to try to write into the same output array, because that they fall in the same bin, and so that's a problem, right? Because we mentioned before that to do that you have to use what is called atomic functions. Atomic execution is, although it's supported in hardware, it's a slow mechanism. So that is what will kill the performance of your histogram application. Does anyone see why the writing in the output is a problem? Because you have this same bin, or let's say you have all both writing on bin 1. So thread number 0 and thread number 50 are going to try to write in the same output location, and that is so the only way you can ensure that happens correctly is by using atomic instruction. Because if you don't use atomic instruction, both the threads might read something and write something else, which will cause it to have an incorrect value. So the atomic instruction, although it's supported in hardware, is a slow process, because the hardware will basically serialize the accesses to that particular element in the matrix, or the particular element in the output array. So this is much different from a vector add, right? In a vector add, each thread writes to an independent location in the output array. But in a histogram, we are not doing that. So that is one of the main reasons why it's somewhat challenging to implement a histogram efficiently. So possible optimizations, you can think of so many different ones, using shared memory, optimizing the histogram using local histograms, and then updating globally. Maybe try to process multiple pixels per thread. Texture memory is another. So texture memory is something that you can take a look at online, and if you have any questions, you can ask me. And the other thing is that you can use something what is called pin memory. So that would be covered next week. And then also use streams for more parallelization. So these two are, if you find them useful, you can use them. But for this week, at least until these last two topics are covered, which will be covered next week, the idea is, you just try to go over the project and see if the things that are mentioned in the project work correctly or not, right? At least I think the CPU version is already implemented in the source code. So I'll upload it, and then you can see if you can just, run the basic algorithm or not. So there are some links here on histogram equalization, and there's a video on YouTube lecture as well. So if you're interested in learning more about the algorithm, you can take a look at that. So the basic idea of the project is, so there are two components to the project, right? So the first thing is that your output should be correct. And the second is the performance should be better. So the person who has the best performance with the correct output is the winner. And I don't know like how many of you know, but normally they give out a GPU. So we are planning to do the same this year as well. And that's depending on, who performs the best. So performance of the application is important, and we'll be evaluating them. So it's important that you run it, or you run your algorithm on discovery, because we'll be evaluating all the algorithms on the same hardware to ensure fairness. But the primary importance is to get the algorithm working correctly, right, before you delve into trying optimizations. So what you can do is, understand the basic histogram equalization algorithm and try to implement like a very simple version. So don't think about shared memory, texture memory, etc. Just try to implement the most simplest version that you can. So it's always important first to start with a simpler version rather than going with complexity, because if you start implementing complex methods, you might get incorrect output, and then the best idea is, again, you already have used the profiler, so you know how to look at what are the profiling metrics, etc. So the idea is, start with a very basic version, record the time, profile it, understand where things are slow, and then gradually try to improve upon it, right? So anyone has any questions?
Did you say the source code for, I guess, the CPU initialization was going to be posted on Piazza?
Yeah. I think the file has the source code for CPU initialization. I have to check, but I think it's there. Yeah. I'm going to post it today or tomorrow. Like also that has the details of the entire project. So it's very similar. The document is similar to how the assignments or the lab assignments look, right?
Okay.
Yeah.
Thank you.
Yeah. And then, for this week, at least before UV covers pin memory and streams next week, the idea is, just try try running the things, right? See if they work, and then you can use the later 2 weeks to run or develop your own optimization. So if necessary, if a lot of people have midterms or etc., we can extend the final deadline by a week as well, but we'll see when we get there. So yeah, that's it for this class. Any other questions? Okay. I think you can stop the recording. Okay.